All right, any volunteers to demonstrate? Yeah, Victoria, please.
Oh, well, I was going to demonstrate.
No, too late. No, you raised your hand.
Wait, no. Well, I was going to say that the pitch gets lower after it goes high.
Well, don't raise your hand when I ask who's going to demonstrate if you're not going to demonstrate, so do it.
It's like zoom. That's not what it's saying.
All right, so Holly, what's the sound like?
It goes
What is wrong with all of you race cars?
Yeah, we need
You
some,
like find the cheapest gas.
we need some voice classes or something.
I can do a race car.
Oh, Alex, you can do it? Great. Alright, well, he did it without laughing. That was an improvement. So we'll hear, I don't know if we're going to hear race cars, but we'll hear some other things that are making the noise that we're having trouble making. But let's visually look a little bit first at what this Doppler effect phenomena is about. What's this thing? Who has good eyesight?
Or a lady.
It is a ladybug. No, I think that's exactly what it is. I think it's a ladybug. And what's the ladybug sitting in? Not a target. Yeah, water, right? Sitting in water. And what's it doing? No, it's not swimming. Not on the left anyway. It's not just sitting. It's floating. It's bobbing up and down, right? It's bobbing up and down and producing, it's causing a disturbance in the water. So the ladybug is creating water waves by moving itself up and down. And just like the tuning fork that we said produces sound that goes in every direction, right? Those waves go in every direction. That disturbance goes in every direction. Well, it doesn't really go up. It might not really go down, but at least it goes out in every direction. So these concentric circles are showing us the crests and troughs that are radiating out from the ladybug. All right, questions about the ladybug hopping up and down and producing these concentric circles that move out? Okay, what is it doing in the picture on the right? Now it's swimming, right? Now it's swimming. And in which direction is it swimming? Point. So about half of you are pointing this way, the other half aren't pointing anyway. I agree with those of you that are pointing towards Mrs. Alvarez's room, right? So the evidence for that, the visual evidence for that, is that the waves that are traveling to the right are getting kind of bunched together because the ladybug's moving in that same direction as she's hopping up and down. The ones that are behind the ladybug are getting kind of spread out, right? And then the ones that are kind of this side and this side, they're not really getting messed with at all. All right, this is what the Doppler effect is a name for, is this phenomena of waves that get bunched together if they're in front of a moving sound source, and waves that get spread out if they're behind the moving sound source. I'm simplifying it a tiny bit. This sound source could actually be standing still, but then whoever's like hearing the sound or detecting the waves could be moving. We'll get into that a little bit more in a few minutes. All right, so the Doppler effect involves a change in frequency and wavelength of waves if we have either the sound source is moving or the detector of the wave is moving. It's not just sound though, it's light, it's water waves, it's any kind of wave that we want to consider. All right, so unfortunately, any of you have like Mavericks on your computers at home? No. So I do, and unfortunately a lot of stuff just still doesn't work with Mavericks, so I had to kind of scramble to find substitutes for a lot of my animations I usually use for this. So what we'll look at first is a video which does a decent job. I'm sure I'll want to interject those some. So let me start playing that. I'll get the lights out, but I'll probably be stopping this a whole bunch.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves.
Right, so there's our ladybug hopping up and down, right?
It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond.
And notice that the waves that are being produced are all of the same frequency, so that's uncommon if we have a real object, but if we have like a tuning fork, that's exactly what we should see, like a single frequency of waves.
Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they're spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect. The apparent
really
change
is all
in
that it
frequency
is.
of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works.
All right, so I have a follow-up question about this. So what I want to know is, in this exact scenario where you're standing in the road, right, the car's honking its horn, I want to know how many different pitches are you going to hear, right? And I'll even make this multiple choice, right? So how many different pitches do you hear in the process of the car coming towards you and then moving away from you? So let's see. Let's say answer A is 1 pitch. Answer B is 2. C is 3. And then D will just say greater than 3. If you think it's an infinite number, then that would obviously be greater than 3. But in your foursomes, can you kind of poll each other what you think the answer is and then attempt to reach agreement?
It's going from an A to an F. Yeah, I think it's more than 4.
Yes.
I think it's infinite.
I think it's infinite because the waves aren't in
Why
front of
don't
each
you
other
wait a
at
few minutes so we can have the most opportune time?
It doesn't like it.
All right, the discussion is waning, so I don't know that everybody reached like a unanimous result, but let's see what you kind of at least had a majority vote for. So Hannah, what did your group end up deciding?
I say more than 3.
More than 3, okay. And Thea, what did your group decide?
More than 3.
More than 3, all right. And Alex, what did your group decide? Same thing. More than 3, all right. And Teresa, what did your group decide? More than 3, okay. And Emily, what did your group decide? 3. All right. Well, I think 3, but let me show you the 3 that I think we're going to hear, and then you guys tell me what other ones you thought we would hear. So I think that we hear a higher than normal pitch right now. All right. So when the waves are bunched up in front of the car, that's higher pitch, right? And then I think we'll hear I'm going the wrong way. I think we'll hear the right pitch, like the pitch that the horn is meant to be playing, as the car passes us. Oh, I lost it. For a brief instant, right? As the actual horn mechanism passes us and we're next to the horn, we're not going to have any Doppler shifting of the wavelength or frequency. And then once the car passes us, where is it? There it goes. Once the car passes us, we'll hear a lower pitch. But there should not be a gradual change. It should be high pitch when it's in front of us, right? Correct pitch for a brief instant when it's next to us, and then low pitch when it's behind us. If that car is traveling at a constant speed, there shouldn't be a gradual change. It should be a sudden change. So anybody want to, now that we've heard my description, anybody want to jump in with why you think there's something beyond the third one? Was it just that you thought it would be a gradual change? Is that what we were thinking? Yeah, right. It shouldn't, if the car's going at a constant speed, it shouldn't be. All right. So let's finish the video, and then we'll get back to this.
So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves mean bluer light, and lower frequency light waves mean redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence of the Big Bang and an indication that the Earth might get very lonely in the distant, distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Alright, so the Doppler shift certainly applies to sound, we can hear that, but it applies to other types of waves. Also, it applies to light, although our eyes aren't great at detecting the small shifts in light frequency and wavelength that we'd be observing there. Right? But our ears are good enough to observe fairly small shifts in sound and frequency. Alright, so Burton, now would probably be a better time. So I have a few other things to play for you that are videos of real sound sources in which we can hear the Doppler effect. So what's that sound like? Yeah, that sounds like a train. Now I hear a horn and a bell. I think the bell kind of stops as the train passes us, so it's really the horn that you want to pay attention to. It definitely just happened. I could have swore I heard it earlier too. So we did hear, right, the lower pitch after it had passed us. Now, one kind of misconception with this, the Doppler shift does nothing to the loudness of the wave. We probably did hear the sound get louder and then quieter, but that was just because the train was closer to us, right? And if it was louder when it was closer to us, it had nothing to do with a shift in loudness or frequency or wavelength. It's just when something's closer to us, it's louder, right? So that was one. I have a couple others. And these have some video as well as audio. What does that sound like? What? A siren like from who? An ambulance or something, right. So we will be able to see the ambulance. Will be traveling this way, and we hopefully will hear the shift in pitch at the same time it passes us. I think it's the back vehicle. Right, so we hear high pitch, and then for an instant we hear regular pitch. It might be so quick that you didn't even really pick that out, and then an immediate shift to low pitch. All right, I have one other, and this one says, oh, I think this is a train. So at about 40 seconds was my note to myself. All right, so this is going to be a train again. Let me just advance to maybe 30 seconds. So it's still pretty far away. It's not that loud yet. So high pitch, I don't know that I heard the regular pitch there, and I heard a very rapid change to a lower pitch sound. Questions about those examples of the Doppler shifting in the pitch of the sound? Yeah, Emma.
Was the train moving at a constant speed?
Say it again.
Was the train moving at a constant speed?
Was the train moving at a constant speed? I don't know, but tell me why you're asking that.
Because I heard more gradual.
Emma thought she heard a gradual change. So one explanation for that could be that it wasn't moving at a constant speed. Now, the other side of that is when I said earlier that we should hear a sudden change, that's really only if we're standing directly in front of the sound source, right? And obviously we're not standing directly in front of it. We get hit if we were standing directly in front of the train. If we're off to the side a little bit, then it actually is going to take a half of a second before we have that total drop. And I think there's a figure in your textbook that kind of shows that pretty well, but you're right, I heard that gradual change also. Yeah, good call. Other issues on those examples before I talk about one other, and then I think I want to look at one other. All right. Anybody have ice cream trucks that kind of like visit your neighborhood? Most of us do. And ice cream trucks usually play music, right? That's how they kind of announce that they're there. It's nicer than just honking your horn, right? And I've noticed that the music sounds good when the ice cream truck's kind of moving towards me, but it sounds bad when it's moving away from me. Has anybody else ever noticed that? A few of you, actually enough of you that I'm convinced that you really did notice it. I think that makes sense, right? The ice cream man, ice cream woman, they don't care what they sound like or look like when you've already bought your ice cream, right? When they're leaving your neighborhood, but they want it to sound good when they're coming, towards your house. So that kind of makes sense that they are adjusting for the Doppler shift to really only sound good when they're moving towards you. I always thought that was kind of interesting. All right, so we do have one other aspect of this Doppler shifting that I think warrants some attention. How fast would you estimate that the train, the ambulance, whatever, were moving? Let's try and do meters per second. Any guesses at how many meters per second? 10, 100, 1,000? 1,000? Anybody think they're going that? No, not 1,000, right? Maybe 20 meters per second, 40 meters per second, 60 meters per second, something like that. When we start moving way faster than that, things can get a little bit interesting, right? So let's move at 300 meters per second. And I'm only talking about sound for right now. All right? So I'm pretty good at, I guess we wouldn't really have a car driving at 300 meters per second. We might have an airplane, all right, flying at 300 meters per second. Where's the noisy part of the airplane? Well, it's going to be like the engine, and where are the engines? I think the engines are actually on the wings, right? So the noise is coming out of like kind of the middle, at least of a commercial airplane. So the airplane's traveling at 300 meters per second. How fast is the sound traveling roughly? Now it's too cold here, so maybe you're sure. How fast is this? Oh, come on, we know this. How fast is the sound traveling? 343 meters per second if it's 20 degrees Celsius air. All right. So the plane's moving at 300, the sound's moving at 343, the waves in front that are moving forward are getting very bunched together. Very, very bunched together. Because the plane is traveling almost as fast as the sound. And the waves that are going this way are getting very spread out. Questions about that severe Doppler shift when we are approaching the speed of the waves? Yeah, Henry.
What if we was moving at exactly?
Right, so let's move at 343 meters per second. That's exactly what I wanted to do next. Okay, so the sound is again coming out of here, but this time the sound source and the sound waves are moving at the same speed. So the waves that normally would go that way, what are they doing? They're getting bunched up right at where they're produced. Right? So they can't travel forward relative to the plane. If they're going the same speed, right? They're covering distance at the same rate. The ones behind are getting really dragged out, but the ones that ought to go in front aren't going in front. We're creating this wall of sound. Jesse?
When that happens, like at the one instant, like when it happens, like
Okay.
isn't there like a...
Well, it would only be one instant if the plane is accelerating from less than the speed of sound to greater than the speed of sound. If it has its cruise control on, it's not just one instant, it's the whole time it's moving. But go ahead, keep going.
Isn't there like a ring that forms around it? It's like, I don't know what it's made of. But...
I think I know what you're talking about, and I think I'm going to show you that after I finish talking in a minute. So yeah, hold on to that. If I don't show it to you, then ask again. Other questions about this wall of sound staying at where the sound is produced if the plane is traveling at the speed of sound. All right, so now let's have the plane go a little bit faster than 343 meters per second. Or just like a little bit faster. So maybe like 350 meters per second. Now the sound that ought to be going in front is going to do what? It's going to be behind the plane, right? The plane is traveling faster than the sound. If Alec and I are, if I'm traveling faster than Alec, I'm going to move in front of him, right? The plane is traveling faster than the sound, so the sound that would have been heading back, backwards behind the plane is still doing that and getting really spread out. The sound that was trying to go forwards is still getting bunched together, but it's lagging behind the plane, right? The plane's moving faster. So if you're in front of this plane, you don't hear a thing until the plane has already passed you, all right? So that's called like breaking the sound barrier, and when we do kind of punch through that wall of sound, we do get a big boom. But even if this region of air reaches us, where we have these waves so bunched together, right? That is a tremendous amount of pressure, a tremendous amount of amplitude in a small region of space. So even if the plane has already poked through the sound barrier and we have this kind of cone of high pressure and low pressure behind it, we're still going to hear a boom, right? So we hear sonic booms when things travel as fast or faster. Really, it's faster than the speed of sound. So I do have a couple of videos to show you about that. I think before I show you the video though, I do have one animated thing. There were a bunch of links on these slides that I didn't show you because they're the ones that just don't work with Maverick yet. So I would encourage you to kind of look at those on your own. All right, so this would be an animation of something that's traveling faster than the sound that it's producing. So we do have the Doppler shifted long wavelength waves behind it, but we also have the Doppler shifted short wavelength waves that aren't going in front of it, they're behind it as well. But it would be like this region here that when we encounter that, we would hear a very loud noise. So here, this is another animation, right, where we have an airplane traveling faster than the speed of sound. And when those waves reach the house, stuff in the house is going to get shaken, fall off shelves, right, rattle around. And we don't really allow planes to do this in populated areas close to the ground, right, because then we do have repercussions from those sound waves. All right, so I have two videos to show you of this happening. Unfortunately, only one of them has audio. I think we'll do the audio one first. Oop, wrong one. Alright, and I think I have them under sound. Yes. Alright, I want this one first. No. I want this one first. Yes. Okay, so this has sound. So let me play it just for a moment so we can see where the heck the plane is. Alright. So the plane is now all the way at the bottom of the screen and kind of traveling up towards the top of the screen. I want you to notice two things. I want you to notice that we hear some wind, but we don't actually hear the plane until after it's past us, and then we do hear a pretty loud boom once those super compressed waves reach us. I think I do it one more time. That's all of this wave energy that's compressed, so we have a lot of amplitude built up in that pretty narrow amount of air.
Wait, Mr. Pincus,
Yeah.
just before it does...
Yeah, I have that better on the next one. I have it better on the next one, so hold on. So the next one doesn't actually have audio with it, but we have some really interesting video. So let me play it through once, and then we'll talk about it. What I saw was a cloud that just like kind of appeared out of nowhere. And then it went away, and then it came back. And when it came back, it formed a really nice cone. right? And Henry, that's what you were going to ask about from the last one, right? Yeah. So Henry saw that in the last one as well. It just the cloud wasn't as thick. It wasn't as pronounced. All right, so I do want to talk about that, but first I need to hear from you guys what the heck a cloud is. Right? So in your foursomes, can you please be ready with an answer for what a cloud is?
Little text like it's in the it's like little droplets of water. And
Oh, okay, most of you are done. Oh, you're not done talking. All right.
yeah, it's just a water cycle. And it like condenses. It gets heavy at the bottom and then it sinks down. Or it gets attracted to the negative or positive energy.
You guys had a green ball. All right, let's compare, and then we'll talk about it. And then I almost forgot to have us hear the Doppler effect at our seats. I think I gave out too many. No. All right. So Julia, what the heck is a cloud?
It's when the water evaporates and then it like condenses and
The water evaporates and then what?
I don't know. It condenses.
Condenses. What does that mean?
It turns into a cloud.
So condenses actually is an important word. So I agree that a cloud is composed mostly of water, but what kind of water?
Okay.
Not water vapor. Water vapor is clear, colorless, we can't see it.
Yes.
Gas is the same as vapor. What? What water just means H2O. Liquid water. Liquid water. Very small liquid water droplets that they're so small that the upward buoyant force is equal usually to their downward weight, right? So they don't actually accelerate down. Liquid water, okay? We can see liquid water, we can't see gaseous water. Now, how do we turn a gas into a liquid? I can think of two ways. Condensation is the name for that process, but I can think of two ways to achieve that. Jesse?
You can put pressure on it.
Okay, but the normal way that we're usually familiar with is to heat it up, right? To increase the temperature until we get to the boiling point, right? But we also can increase the pressure, and then that can cause the boiling point to be low enough to condense the gas into liquid at a pretty low temperature. And that's exactly what happened in this video, right? The plane made liquid water where there was only gaseous water, but it didn't do it by increasing or by decreasing temperature. It did it by increasing the pressure due to the sound that was building up at it, right? And when it was passing, we actually saw this really nice cone shape that we saw in the animation a couple of minutes ago, right? So that's showing us that shock wave. It's showing us that high pressure sound that was building up that can't travel in front of it, which kind of lingers right behind it a little bit if it's traveling close to the speed of sound. Speed of sound is called, Mach 1 means we're traveling at the speed of sound, right? You probably heard that. That just means we're going at whatever the sound of whatever the speed of the sound is in the air that time. Other questions about that video? All right. Before we move on, I'd like each person in your group to strike the tuning fork against the green thing, right, and just move it back and forth next to your ear to hear the alternating high pitch and low pitch. Make sure that you do move it this way though, not that way, right? So hear that, and then we'll recollect that. And I think did I give you guys? No, I didn't. All right, here.
It's like, when you get pet algae, this is what it feels like pet algae.
What's wrong with it? I'm gonna miss it.
I want to put
Okay, only green, only green. You gotta move it pretty fast, Henry. All right, so all four, you all heard it?
No, it doesn't help it.
Jesse's being a tuning fork hog.